Hi guys, I did the complete reverse engineering of this unit, 4 boards. So this is the input board which is connected to the PMT. Here we can see the PMT here and the high voltage power supply. The power supply is negative here. This is the cathode of the PMT and this is the anode. The anode is connected to two different circuits. The main circuit is this one. There is an AC coupling. There is a bandpass filter, 100 Hz. The signal is fed to this amplifier with a voltage limiter here, and the output here is fed to a comparator. At the output there is a square wave, and this square wave is fed to the phase detectors we have seen in the previous episode. And we can see that there is also another circuit here which permits to monitor the signal of the PMT. We can see also that the output of the PMT is connected to the second circuit here. The input voltage is negative, of course, so this circuit is a logarithm amplifier which permits to have a measurement of the ambient light. We can see that we have a voltage follower here connected to one pin of the power supply. We have probably a monitoring of the high voltage power supply. I suspect that there is a resistor from that point to here in order to have a voltage divider. Here there is a trimmer which permits probably to adjust the high voltage power supply, and there is a transistor which permits to commute this line to plus 12 volts approximately, or left open when this transistor is off. Okay, I'm going to turn on the power supply. We should see a signal at 100 Hz which comes from the neon lights. On the scope we have two signals, the PMT signal here and the ambient light. Okay. And we can see here the variation of light. You can see that this thing is very sensitive. Okay, we can see here the ambient light. You can see that this thing is incredibly sensitive. I have connected this bulb for an infrared source. You can see the phase shift. It was working last week, but I have lost one reference signal here. Actually one op-amp is dead, this one is okay. But there is nothing at the output of the second op-amp. I will replace it by a modern one. It was impossible to remove this old op-amp, AD511B. Therefore I have placed this LF351 over it. Okay, so we can see that we have retrieved the reference signals, sine and cosine. There is a phase shift of 91 degrees. I have connected the outputs of the phase detectors, this one and this one, to the oscilloscope. Unfortunately, this unit doesn't work anymore. There is a voltage close to zero. I suspect that this high voltage power supply doesn't work anymore, so I will try to repair this power supply. It will be complicated because this thing is spotted. We have here the PMT and the high voltage power supply assembly. The serial number of this one is 21, the model 6872, PMT 5153. Okay, so we have here actually the power supply assembly. So I suspect that some wires are connected to the socket of the PMT. Other wires penetrate inside the power supply assembly. I think it is possible to remove this power supply from the rest. I guess that we have here the high voltage power supply, which is negative. The white wire corresponds to the power supply adjustment. The shielded cable here corresponds to the anode. The gray wire permits the measurement of the high voltage. There is a resistive divider, and the cathode is this black wire. Unfortunately, it is impossible to remove the PMT itself from the shield. And we have here the power supply assembly. I think it is possible to disassemble this unit. There is a metal plate here. I have connected this power supply unit to a power supply, but the power supply current is null, so I think that this power supply doesn't work. Okay, so we can see the potting, and it is a hard potting. It is possible to get access to this part here. It is very complicated. You can see that there are several transistors here. We have here the regulation circuit, and here the high voltage section. We can see that there is a transformer. So we can see here several resistors. I guess that these resistors are used for the feedback. And you can see the feedback connection here. The high voltage output is here. I think that the best solution is to cut here. And I hope that the issue is on this section and not on the high voltage section, because it is impossible to get access to the parts. Next step will be to do the reverse engineering of this controller. I did the reverse engineering of this high voltage power supply controller. The schematic is here, so this is interesting. There is the first regulated power supply here, something which is very common back in the day. And there is here a differential amplifier. It uses 3 pairs of transistors. I cannot read the part type of this transistor, it is erased. So this is actually an op-amp. There is a Darlington here. So this permits to have a very low bias current. One input of the differential amplifier is connected to board SK4. This is an extract of that board. There is an adjustment of that voltage. And the second input is connected to the high voltage unit. Obviously, we should have a resistor connected between the negative high voltage output here and the feedback output. Here there is a reference voltage, and this thing is stabilized when this voltage equals this one. So this permits an adjustment. So therefore the output voltage can be adjusted by this trimmer on board SK4. And you can see that this unit is supplied with a DC voltage. The output of the differential amplifier here is fed to this transistor, which drives this Darlington, and the emitter drives the high voltage unit. So therefore it is possible to test this high voltage unit by applying a DC voltage between green and white wires. And at the output we should have a negative voltage, which is more or less proportional to the power supply voltage here. I have connected this high voltage unit to a DC power supply. Currently the voltage is 7 volts, and this DMM monitors the output voltage. I am going to turn on the power supply. Okay. So there is a voltage of minus 861 volts for 7 volts. So let's increase the power supply. There is an output voltage of minus 1 kilovolt for a DC voltage of 8 volts. Okay, on that line here. Okay. 4 volts minus 500 approximately. So this thing is linear. It is also interesting to measure the resistance of this feedback resistor. The resistance is 48 megohms approximately. I have connected this board to a power supply 24 volts. I think there is at least an issue with this power supply. There is a voltage of 4 volts here. Obviously it is not enough, so it seems that there is an issue with this power supply. Okay, 3.8, it is not stable. I have removed these 4 transistors here. I have measured the Zener voltage of this diode. It is 5 volts. We can see that there is an attenuation by a factor of 3 approximately. So therefore we should have on that point a voltage of 15 to 16 volts approximately. So there is probably an issue with one or several transistors. So therefore I will change all of them. So I have changed these 4 transistors, and I have the same thing. Okay, so I have repaired this module. I have divided by 10 these values, 20K and 47K. I have also changed this value 100K instead of 470K. And this thing works. There is a voltage of 18 volts approximately. And you can see it is possible to adjust the output voltage with this potentiometer. It is a little bit unstable, but it will be okay for a quick test. For the final test, I have connected the oscilloscope X and Y mode to these 2 outputs here. we should have a spot here. The location of the spot here should correspond to the location of the infrared light here.